Hi everyone. Welcome to Chapter 3 of our course, Introduction to Computer-Aided Design, often abbreviated as CD. This chapter is designed to introduce you to the fundamental concepts of CAD and to get you familiar with SolidWorks, a powerful CAD software. Here's a quick look at what we will be covering in this first part of Chapter 3. We'll start with an introduction to SolidWorks, understanding what CAD is and its applications. Then we will delve into SolidWorks models, discussing the different types of files you'll encounter. Following that, we will explore the SolidWorks concept, which includes parametric modeling, feature-based design, and associative modeling. We will also spend significant time on design intent, which is crucial for creating robust and adaptable designs. The latter topics, basic terminology, user interface, and mouse gestures, will be covered in Part 2 of this chapter. So for today we're focusing on topics 1 to 4 as part of Fundamentals of Computer-Aided Design and SolidWorks Overview. So, let's proceed to the first part of Chapter 3, Fundamentals of Computer-Aided Design and SolidWorks Overview. By the end of this specific part of the chapter, students should be able to explain the concept of computer-aided design, identify the key features of SolidWorks software, and demonstrate an understanding of parametric modeling, feature-based design, and design intent in creating basic 3D models. Let's begin with the fundamental question: what is computer-aided design? In simple terms, CAD refers to the use of computer software to assist in the entire design process. This includes creating, modifying, analyzing, and optimizing a design. Think of it as a digital drafting board but far more advanced and efficient. It replaces traditional manual drafting methods, allowing designers and engineers to create incredibly precise 2D drawings and 3D models of products or systems. CAD software comes with several key features that make it indispensable in modern engineering and design. Accuracy. It offers very high precision in dimensions and geometry, meaning your designs will be exact. Efficiency. It allows for much faster design iterations and modifications. Imagine having to redraw an entire blueprint every time you make a small change. CAD eliminates that. Visualization. You can create realistic 3D renderings and even simulate how your design will look or behave in the real world, long before it's manufactured. Documentation. CAD can automatically generate important engineering documents, like detailed drawings, bill of materials which list all the parts needed and specifications. Integration. It easily integrates with other computer-aided tools such as CAM, which stands for Computer-Aided Manufacturing, and CAE for Computer-Aided Engineering. This creates a seamless workflow for complete product development. So, where do we see CAD being used in the real world? Its applications are vast and span across numerous industries. In product and industrial design, CAD is widely used to design consumer goods and industrial products, focusing on how they function, their appearance, and how easily they can be manufactured. For example, it's used for designing car components like dashboards or engine parts, aircraft structures and turbine blades in aerospace, and even everyday consumer goods like electronics casings, kitchenware, and sports equipment. In mechanical design and assemblies, CAD is absolutely essential for creating precise mechanical parts and putting them together into assemblies. This includes designing gears, bearings, and fasteners as well as complex machine parts and tools. You can even simulate how these assemblies move and check for any parts that might interfere with each other. In architecture and civil engineering, CAD is used for drafting floor plans, structural layouts for buildings, and even planning large-scale infrastructure like bridges, highways, and urban areas. It integrates seamlessly with building information modeling or BIM tools, which are advanced systems for managing building project data. In polymer product development, CAD is vital for designing products made from polymers like plastics and the tools used to manufacture them. This includes packaging such as bottles and flexible films, biomedical devices like prosthetics, and the design of injection molds and dies. You can even simulate how materials flow during the manufacturing process and how parts cool down. With the wide range of industries and applications relying on computer-aided design, it's no surprise that there are many different CAD software tools available, each tailored with its own strengths and capabilities. Whether it's for architectural blueprints, mechanical components, or polymer product simulations, Choosing the right software often depends on the specific needs of the project and the industry involved. Let's begin with general-purpose CAD software, which is commonly used across multiple fields, including architecture, mechanical engineering, and industrial design. AutoCAD is one of the most recognized names in this category. It has long been considered the industry standard, particularly for 2D drafting. While it also offers basic 3D modeling capabilities, its strength lies in producing precise and efficient technical drawings, making it a staple in architecture, civil, and mechanical engineering workflows. Next is Fusion 360, a modern cloud-based platform developed by Autodesk. Unlike traditional software that runs entirely on a local computer, Fusion 360 operates primarily over the Internet. It combines 3D CAD design, computer-aided manufacturing, and computer-aided engineering into one integrated tool. Fusion 360 is ideal for product design, rapid prototyping, and simulation work, and it has gained popularity in academic settings due to its accessibility and user-friendly environment. Our main focus in this course, however, is SolidWorks. SolidWorks is a powerful parametric 3D modeling software that is especially popular in mechanical and product design. It is feature-based and highly intuitive, allowing users to create precise models with design intent in mind. Its wide adoption across engineering industries, including polymer technology, makes it an essential tool for anyone working in modern product development. The software also supports simulations, assemblies, and detailed 2D drawing generation, making it a comprehensive solution for design and documentation. Another versatile tool is Rhino 3D, which excels in industrial and artistic design. Unlike the strictly parametric nature of SolidWorks, Rhino is known for its ability to model complex and organic freeform surfaces. It is frequently used in fields like biomedical design, such as custom prosthetics, as well as in jewelry and product design that require aesthetic, flowing shapes. For more advanced needs, especially in high-precision industries, we have CATIA. Developed by Dassault Systems, which is the same company behind SolidWorks, CATIA is extensively used in aerospace, automotive, and marine design. It offers robust tools for surface modeling and systems engineering, making it suitable for designing large and highly intricate assemblies. Similarly, Creo, formerly known as ProEngineer, is another high-end 3D CAD software used widely in industrial product development. Known for its solid parametric foundation and advanced capabilities, Creo is suitable for complex mechanical designs and engineering analysis in sectors such as machinery, electronics, and manufacturing. When it comes to polymer and product design, we often require specialized simulation tools that go beyond simple 3D modeling. One such tool is SolidWorks Plastics, which is an add-on to the SolidWorks platform. It allows engineers to simulate the flow of molten plastic during the injection molding process. This helps in identifying defects such as air traps, weld lines, or improper filling before the physical mold is even made, saving time and cost. Another advanced simulation tool is Moldex 3D. This software is dedicated to the polymer processing industry and is used for analyzing plastic injection molding in great detail. It supports a wide range of materials and processing conditions, making it a preferred tool for research and industrial applications where accuracy in flow, cooling, and warpage analysis is critical. Now let's take a closer look at SolidWorks, the software that will be central to your learning and design work throughout this course. SolidWorks is a professional 3D computer-aided design software widely used for creating, simulating, and documenting mechanical components, assemblies, and engineering drawings. Developed by Dassault Systems, SolidWorks has become one of the most trusted and extensively adopted tools in industries such as mechanical engineering, manufacturing, automotive, aerospace, and product design. What makes SolidWorks so powerful is its combination of user-friendly interface with robust modeling capabilities, making it suitable for both beginners and experienced designers. It is built on a parametric feature-based modeling system, which means you can create designs that are not only accurate but also flexible and easy to modify. Whether you're sketching a basic part or assembling hundreds of components, SolidWorks gives you the tools to do so efficiently and precisely. If you look at the diagram on the slide, you'll see that SolidWorks offers a wide range of capabilities that extend beyond basic 3D modeling. At its core is mechanical design, where SolidWorks truly excels. It enables users to design individual parts as well as complex mechanical systems, complete with moving components and detailed subassemblies. From gears and shafts to enclosures and brackets, SolidWorks allows you to bring your mechanical concepts to life. But it doesn't stop there. SolidWorks also includes electrical design tools, which are essential for modern products that combine mechanical and electronic systems. These tools allow for the integration of wiring, circuits, and control systems directly into your 3D models, ensuring better coordination and fewer errors between electrical and mechanical teams. Another critical capability is simulation. With SolidWorks simulation, you can test how your designs will perform under real-world conditions, such as load, pressure, temperature, and even fluid flow. This virtual testing helps you identify weaknesses or inefficiencies before building physical prototypes, saving both time and cost in product development. SolidWorks also supports data management, which is especially important in large-scale projects or team environments. It allows you to keep track of design versions, manage file relationships, and control access to ensure that everyone is working on the most up-to-date data. This is vital in collaborative design settings where accuracy and coordination are key. Lastly, communication is made seamless with SolidWorks. The software provides tools to generate realistic renderings, exploded views, animations, and detailed drawings that effectively communicate your design to clients, stakeholders, or manufacturers. These outputs help bridge the gap between idea and production by making technical content easy to understand. Building on what we've discussed in the previous slide, let's explore the widespread application of SolidWorks across different industries. The diagram on this slide visually reinforces just how far-reaching and versatile this software is. SolidWorks isn't limited to a single field or product type. It is a multifunctional design platform that supports a wide variety of industries, each with its own unique challenges and needs. In the automotive and transportation sector, SolidWorks is used extensively to design everything from individual vehicle components to complete systems. Whether it's suspension parts, dashboards, or engine components, the software provides the precision and simulation tools needed to ensure performance and safety. Its ability to manage large assemblies makes it a favorite in this fast-moving, innovation-driven field. Another key area is design and engineering services. Many companies offer design consulting or contract-based engineering support to multiple clients across industries. These firms rely on SolidWorks because of its flexibility, collaborative tools, and broad file compatibility. The software enables them to quickly adapt to different project requirements and deliver professional results efficiently. SolidWorks also plays a critical role in the alternative energy sector. As demand grows for sustainable solutions, engineers use SolidWorks to design and optimize components for systems like wind turbines, solar panel structures, and energy storage units. Simulation features help test these components under environmental conditions to ensure reliability and efficiency. In the field of consumer goods, SolidWorks is behind the design of countless everyday items, from kitchen appliances and home electronics to wearable devices and toys. The software supports both aesthetic surface modeling and engineering functionality, making it perfect for creating products that are both visually appealing and mechanically sound. When it comes to industrial and packaging machinery, SolidWorks shines in handling complex assemblies and moving parts. Engineers use it to model conveyor systems, automated lines, robotic arms, and packaging equipment. The ability to simulate motion and interference detection is particularly useful in this field, where timing and mechanical precision are essential. The medical industry is another area where SolidWorks proves its value. It is used to design medical instruments, implantable devices, diagnostic tools, and prosthetics. With tight regulatory requirements and the need for patient-specific customization, the precision and control offered by SolidWorks are critical. And of course, this is just the beginning. SolidWorks is used in aerospace, marine, construction, agriculture, and education, among many other sectors. Its ability to adapt to different engineering demands makes it one of the most powerful tools in the design world today. When working in SolidWorks, you'll primarily be dealing with three main types of files, often referred to as models. Each file type serves a specific purpose in the design and documentation process and follows a structured workflow from concept to production. The first and most basic type is the part file. A part is a 3D representation of a single design component, essentially one standalone piece of a larger product. Think of it like one puzzle piece in a much bigger picture. For example, a bolt, a gear, or a bracket would each be modeled as an individual part. These files are saved with the extension .sldprt. In practice, every unique physical item in your final product usually begins as its own part file. The second type is the assembly file, which is where the true power of SolidWorks starts to come together. An assembly is a 3D environment where multiple parts, and even other subassemblies, are brought together and connected to form a complete system or product. For instance, if you're designing a bicycle, the frame, wheels, chain, pedals, and handlebars would each be modeled as separate part files. These parts would then be combined in an assembly file, allowing you to see how the components fit and interact. Assembly files use the extension .sldasm. In assemblies, you can apply relationships known as mates to align, fix, or allow movement between parts. The third and final file type is the drawing file. A drawing is a 2D representation created from a part or an assembly. It provides the technical details required for manufacturing, such as dimensions, tolerances, annotations, material specifications, and multiple views: front, top, side, and isometric. These drawings act as blueprints or instruction sheets that guide fabricators or machinists in producing the actual physical product. Drawing files are saved with the extension .slddrw. Together, these three file types, part, assembly, and drawing, form the foundation of most workflows in SolidWorks. Understanding how they relate to one another and when to use each is essential for efficient, professional-level design work. This slide offers a clear visual summary of what we've just discussed regarding the three main SolidWorks file types: part, assembly, and drawing. At the top left and right of the slide, you can see two separate parts. These are individual 3D components modeled independently. Each part represents a single, standalone element of a product, such as a bracket or a housing, and is saved with the file extension .sldprt. These parts form the foundation of any design project in SolidWorks. Moving to the center of the slide, you will see an assembly, which is where those individual parts are brought together into a complete unit. In this example, the two parts have been combined in an assembly file to represent a functioning product or mechanical system. Assemblies allow designers to test fit, movement, and relationships between components through mating and constraint tools. At the bottom of the slide, you will notice two examples of drawings, generated from the part and assembly models. These drawing files contain detailed 2D representations of the models, including multiple views, such as top, front, side, and isometric, as well as precise dimensions, annotations, and title blocks. These are the documents that would typically be used for manufacturing and quality control. Altogether, this slide illustrates how SolidWorks enables a seamless workflow, from designing individual components, to assembling complete products, and finally producing professional engineering drawings. It demonstrates how all three file types work together to support the full product development cycle in a single integrated platform. Now let's move on to the core philosophy behind SolidWorks, the foundation that makes it such a powerful design tool. SolidWorks is built on three main concepts: parametric modeling, feature-based design, and associative modeling. These three ideas help define how your designs behave and how easily you can make changes. With parametric modeling, your model is controlled by dimensions and constraints, so it updates automatically when values change. Feature-based design means you build your model step by step using features like extrude, cut, and fillet. And with associative modeling, changes made to a part are automatically reflected in the related assemblies and drawings. Together, these concepts support what we call design intent, which is the idea that your model should react intelligently when modified. We will explore each of these in more detail in the upcoming slides. Let's begin with the first core concept of SolidWorks: parametric modeling. In parametric modeling, your design is controlled by parameters, which are measurable values like dimensions, constraints, and geometric relationships. These parameters act as the driving force behind the shape and behavior of your model. The key advantage is that when you change any one of these parameters, such as the length, width, or diameter, the model automatically updates to reflect the change. This makes the design process far more dynamic and efficient. What makes parametric modeling so powerful is that it allows for easy revisions without having to redraw the entire part. That's why it's often referred to as smart modeling. Instead of creating rigid static drawings, you're building flexible models that respond to changes. This capability not only speeds up your workflow, but it also helps reduce errors, especially when you're working on complex or evolving designs. It makes your models future-ready, allowing for modifications as requirements change. Let's look at a simple example to illustrate how this works. Imagine you are designing a plastic container that always needs to be twice as long as it is wide, and the height remains fixed at 50 millimeters. In a parametric model, you would set up the following relationships. Width equal 40 millimeters. Length equals width times 2, which would be 80 millimeters. Height equal 50 millimeters. Now let's say you decide to change the width to 60 millimeters. Because of the defined relationship, SolidWorks will automatically recalculate the length to be 120 millimeters, while the height remains unchanged at 50 millimeters. There's no need to manually adjust each value or redraw the box. SolidWorks does the work for you. This simple example highlights the strength of parametric modeling. Your design is no longer just a static drawing, but a responsive system that adapts to changes with minimal effort. This is the foundation of efficient, professional CAD modeling. Next, let's look at the second core concept in SolidWorks: feature-based design. Unlike traditional drafting where you manipulate individual lines and arcs, SolidWorks focuses on building models using features. A feature is a fundamental shape or operation that either adds or removes material from a 3D model. This method allows you to construct parts in a structured, step-by-step way, where each feature builds on the last. Some common examples of features include extrude, which pushes a 2D sketch into a solid 3D shape; revolve, which spins a sketch around an axis to create round or cylindrical parts; and cut, which removes material from a solid body. You will also frequently use features like fillet, which rounds off sharp edges for smoother transitions, and chamfer, which bevels corners at a defined angle and distance. All of these features are organized chronologically in a powerful interface tool called the Feature Manager Design Tree, which you can see illustrated on the slide. This design tree acts like a history log of how your part was created, from the first sketch all the way to the final detail. Each feature is listed in the order it was applied, and you can click on any feature to review or modify its parameters. What makes this approach especially useful is that you can easily go back and edit any feature at any time in the design process. When you make a change, SolidWorks will automatically update all the other features that depend on it. This saves you from having to rebuild your model from scratch and significantly reduces errors, especially in complex designs. The third core concept in SolidWorks is associative modeling. This concept refers to the smart connection or associativity that SolidWorks maintains between different file types, specifically your part files, assembly files, and 2D engineering drawings. This built-in associativity is a powerful feature that ensures consistency across your entire project, saving time and greatly reducing the risk of errors. Let's break this down with two common examples. First, consider the connection from part to assembly. Imagine you've created a bracket as a part file and added it into several assemblies. If you later decide to change the diameter of a hole in that bracket, every assembly that includes that bracket will automatically update to reflect the change. You don't have to go into each assembly and make the same edit manually. This automatic update keeps your designs consistent and dramatically speeds up the revision process. Now for the second example: assembly to drawing. Let's say you've created a detailed 2D drawing of your assembly. If you go back and make changes to a part or even the assembly layout, such as repositioning components or adjusting dimensions, all the related drawings update automatically. This includes updated dimensions, new view orientations, and any annotations linked to the geometry. The result: your 2D drawings are always synchronized with your latest 3D model, which helps prevent costly manufacturing mistakes caused by outdated documentation. Now let's talk about one of the most critical concepts in CAD modeling, which is design intent. Design intent refers to the strategy and logic you build into your model that determines how it should behave when changes are made. It's not just about drawing a shape, it's about teaching your model how to think and respond. When you modify dimensions, move features, or adjust parameters, a model with well-defined design intent will adapt automatically and correctly, without breaking or producing unexpected results. So why is design intent so important? First, it ensures consistency throughout your design. When your model is structured with intent, similar elements will behave predictably even as changes are made. Second, it saves you a tremendous amount of time. Instead of having to redraw or manually fix geometry after each revision, your model will update intelligently. And most importantly, it creates designs that are smart, flexible, and easy to modify. A major advantage in real-world product development where changes and refinements are constant. SolidWorks provides several tools to help you capture and apply design intent in your models. These tools make sure your design behaves correctly when changes are made. One of the most basic tools is geometric relations, which control how sketch elements relate to each other. For example, keeping lines vertical or equal in length. Then there are parametric dimensions, which are the numerical values that define the size and position of your features. You can also use equations and global variables to link dimensions or reuse important values across your model. For more complex designs, reference geometry like planes and axes help position features accurately and maintain symmetry. Lastly, configurations let you create different versions of a part or assembly in one file by changing dimensions, features, or materials. We'll look at each of these tools in more detail next, but just remember, all of them work together to help you design smarter, faster, and with fewer errors. Let's dive deeper into geometric relations, one of the fundamental tools for design intent. These relations are applied during sketching and are essential for controlling the shape and behavior of your geometry. Think of them as rules or constraints that define how different sketch elements should behave relative to one another. Geometric relations allow your sketches to remain consistent, even when dimensions or features are changed later. Instead of manually aligning or adjusting lines and shapes, you can apply these relations to let SolidWorks automatically maintain the intended geometry. Some of the most common types include horizontal and vertical relations. These ensure that lines stay perfectly aligned with the horizontal or vertical axes, keeping your sketches clean and precise. The equal relation is another frequently used tool. It forces two or more lines or circles to always have the same length or radius, which is very helpful when designing symmetrical or repeating features. Then we have parallel and perpendicular relations. These maintain angular relationships between lines. For example, if you want two lines to always run side by side, apply a parallel relation. If you want them to meet at a right angle, apply a perpendicular relation. And SolidWorks will maintain that 90-degree relationship even as you move or scale other parts of the sketch. Another powerful relation is coincident, which ensures that a point lies exactly on a line, arc, or another curve. This is useful when you want to snap the endpoint of a line to the edge of a circle, or to the midpoint of another line. Similarly, the collinear relation keeps two lines aligned along the same infinite path, ideal when you want multiple segments to form one continuous straight line. The table on the slide clearly demonstrates how applying these relations changes the geometry, showing the before and after states. Another essential aspect of design intent in SolidWorks is the use of parametric dimensions. These dimensions are what control the size and position of the elements in your sketch or 3D model. Unlike manual drafting where you might simply draw something to look correct, parametric dimensions ensure that every line, arc, or feature is defined by an exact numerical value. This allows your model to be precise, flexible, and easily editable. There are two main types of parametric dimensions in SolidWorks: driving dimensions and driven dimensions. A driving dimension is the primary type. It is the dimension that you define. It directly controls the geometry. For example, if you draw a rectangle and enter a value of 100 mm for its length, that input becomes a driving dimension. It tells SolidWorks exactly how long that line should be, and any changes to this value will directly affect the shape or size of the object. On the other hand, a driven dimension is automatically calculated by SolidWorks based on existing driving dimensions and geometric relations. You cannot change a driven dimension directly. Instead, It updates automatically whenever related driving dimensions are changed. For example, if you have already defined the total length of a shape and set the position of 2 points, SolidWorks might calculate the remaining segment as a driven dimension. This type of dimension helps you maintain design accuracy and consistency, especially in more complex sketches where too many driving dimensions could overconstrain the model. Moving on to the more advanced tools for capturing design intent in SolidWorks, let's take a look at equations and global variables. These features allow you to introduce mathematical logic and reusable values into your models, making your designs not only more intelligent but also highly adaptable and easy to manage, especially as they grow more complex. Equations are mathematical expressions that define the value of a dimension or a feature parameter. Instead of entering fixed values, you can create equations based on other dimensions, global variables, or mathematical functions. For example, you might set the depth of an extrusion to always be half the width of a part by using an equation like equals width/2. You can also use equations to control other aspects of the design, such as the radius of a fillet or whether a certain feature is active or suppressed, based on conditional logic. This creates a dynamic model that adapts automatically when any driving value changes. Complementing equations are global variables. These are user-defined names that hold numerical values. Think of a global variable as a named constant or universal input that you can refer to multiple times across your model. For example, you might define variables such as plate thickness equals 5, hole diameter equals 10, or gap clearance equals 2. Once defined, these variables can be linked to multiple dimensions or equations throughout your part or even reused in related assemblies. When you update the global variable in one place, every related value across the model updates automatically, keeping everything consistent and saving a significant amount of time. Let's move on to another powerful design intent tool in SolidWorks: reference geometry. This tool becomes especially important when you're working with more complex parts and assemblies. Reference geometry consists of invisible helper elements. They don't become part of your final solid model, but they are essential for building and positioning other features accurately. You can think of them as the invisible scaffolding that holds your design together, helping to guide and anchor features in a controlled and predictable way. There are several types of reference geometry in SolidWorks, each serving a specific purpose. One of the most commonly used is the plane. A plane is a flat, infinite surface that can be used as a sketching platform or as a boundary for a feature. For example, if you need to sketch a feature at an angle or a specific offset from an existing face, you would create a reference plane in the required orientation or location. Planes are also commonly used to create symmetry in parts by serving as mirror planes. Next we have axes. An axis is an imaginary straight line that's often used as a reference for circular features. You might use it to revolve a sketch into a 3D shape, such as creating a pipe or a cylindrical shaft. Axes are also useful when establishing concentric relationships, ensuring holes, slots, or other features align perfectly around a common centerline. Another helpful type of reference geometry is the point. A point marks a specific location in 3D space, which can serve as a target for placing features, defining hole centers, or constraining geometry. For example, you might place a point at the center of a circular pattern or use it to define where a hole should be drilled. Lastly, we have the coordinate system. This is a tool used to define the orientation and origin of your model, especially useful when working with imported files, assemblies that require precise alignment, or during advanced simulations. While not used as frequently in basic modeling tasks, coordinate systems play a vital role in multi-body modeling, data exchange, and engineering analysis. Using reference geometry effectively ensures that your model is robust and responsive to change. For example, if you build a plane offset from a face and then later modify the size or angle of that face, the offset plane will automatically adjust, along with any features sketched on it. This ability to maintain relationships and update predictably is a core part of preserving design intent. Finally, let's take a look at configurations, one of the most powerful and efficient features in SolidWorks for managing multiple versions of a design. Configurations allow you to create different variations of a single part or assembly within one file. This is incredibly useful when you need to model products that share a common base design but differ in size, features, or materials. Imagine you're designing a screw that comes in 3 different lengths: 10 mm, 20 mm, and 30 mm. Instead of creating 3 separate part files for each length, you can use configurations to store all these variations in a single .slidprt file. This keeps your project organized and dramatically reduces the number of files you need to manage. So, how do configurations work? You can define them by changing dimensions, suppressing or unsuppressing features, or even applying different materials, all within the same file. Each configuration acts like a custom version of your model, but it's still linked to the same core geometry. This means you only have one master file, but multiple design variations at your fingertips. To better understand this, let's consider a more complex example: designing a chair. In a single part file, you could create multiple configurations. First, a dining chair configuration with a standard seat height. Second, a bar stool configuration with a taller leg height. Third, a chair with armrests configuration where the armrest features are turned on. And fourth, a chair without armrests configuration where those features are turned off. All of these versions would exist within one file, allowing you to switch between them instantly, make updates easily, and avoid cluttering your system with separate files for each variation. This is especially beneficial when designing product families or when presenting multiple options to a client or team. In summary, configurations help you work smarter by managing design variations in a single location. They enhance your productivity, reduce errors, and give you more flexibility when designing customizable or modular products.